Let's do a little review. I'm just going to work through the odd solutions on our final exam, Chapter 6 review guide here. So basically the left-hand column for most of this here. So the first one's a good example of looking for perfect squares that divide in evenly. In this case, 36 times 2 is 72, so you can take the square root of the 36 part, leave the square root of 2 behind, so that's just 6 square root of 2. So that's kind of the best way to do these if you can find a perfect square that divides in evenly. I'm going to switch over to black ink here. Actually, stay red. This next one, though, is a little bit different because it's kind of hard to look at that one and say, oh, there's a perfect square that divides in evenly into that. Maybe 4, you could start with 4, but then you got to do a lot of little work. Now, I probably won't give you one this big on the test itself, the exam itself, but this is a good one to practice with using this prime factorization method, and this is the one where you take 384 and you start dividing the smallest prime factors into it possible. So it's even. I'm just going to start dividing by 2. If you divide that in there, it goes in, what, 1, 9, and 2, 192 times. And I can divide that by 2. Again, that goes in 96 times. I can keep dividing by 2 until I can't divide by 2 anymore. Just keep going here. 2 divides into that 12 times. 2 divides into that 6 times. 2 divides into that 3 times. So I count up all my 2's here. I've got, what, 1, 2, 3, 4, 5, 6, 7. So that's 2 to the 7th. And then I got 1, 3 at the end. So what you do is you rewrite this problem, I'll rewrite it in black, as 2 to the 7th times 3 that we're going to take the square root of. So remember, when you're doing square roots, it's like there's a little 2 there, and you're really seeing how many times you can divide that 2 into each of these powers. Now this is a 3 to the first here, keep that in mind. So 2 divides into 7 3 times, so that means I can take out a 2 to the 3rd power here. Okay, that's what the 2 to the 7th is after you take square root of that. But there's 1 left over, okay? So there's a 2 left over inside, or 2 to the 1st in there. I can't divide 2 into this 1 here at all for the 3, so that also stays inside. So it has to divide in evenly, and however many of those you take out, that's your power on the outside. So I can rewrite this as 2 to the 3rd being 8, and the square root of 6 after I multiply those two guys together. So that's kind of our fallback method. If you can't see a perfect square that divides in evenly, you can always just prime factorization, and it turns it into kind of one of the problems with the variables. Next one here, 32 is 2 times 16, so I'm going to rewrite this as -5, and this is 16 times 2 here. Now don't worry about that -5, just leave it out there. We'll multiply it by whatever the square root of 16 is, which is 4. So I just took the square root of 16, but the square root of 2 stays in there. So now I multiply these together to get -20 times the square root of 2. All right, taking a look at this next one. Now we've got some variables involved. Now let me just rewrite this as, really we're going to work this as square root of 256 times the square root of u times the square root of v to the 4th. That's really how you want to treat these. It's basically 3 separate problems. Square root of 256, that's one of those ones I said it's good to know. 16 squared is 256, so this is just 16. The square root of u, can't do anything with it, but you can take the square root of v to the 4th. Remember, 2 is our root there, so it divides into the 4 twice. That means I've got a v squared on the outside. But the u, nothing I can do with that. That just stays put. All right, let's try another one kind of similar to that. You know what, this is I'm not going to worry about number 9 here. I'm probably not going to give you a 5th root or a negative here, just because it's a little bit bigger than I wanted. I will focus on just this one right here, x to the 7th. If I was just doing that part of this one, the 5th root of x to the 7th, it's just how many times does 5 divide into 7? Divides into once. But there are 2 that remain. So you're really just doing, when you have problems like that, you're saying, well, take your power divided by the root. That's 1 with a remainder of 2. So literally 2 remains in there while you take 1 out. That's kind of the process there. All right, next one here, starting to get into the adding and subtracting. Okay, so when you add and subtract these, you can only add and subtract like terms. So the only like terms I have are the ones that have the square root of 2's in them. I can't do anything with this minus square root of 3. All right, that's just going to be tacked onto the end of this answer. But I'm going to put these two guys together. But remember, this is, let me get rid of these here. This is the same as minus 1 square root of 2. So treat this like it was a problem like minus 3x minus x. That would equal negative 4x, right? So that's exactly what you do here. You say negative 1 or negative 3 minus 1 is a negative 4 square root of 2. So you have negative 4 square roots of 2. But the minus square root of 3, it's not a like term. You know, square root of 2, square root of 3, treat it like it's an x and a y. You can't combine them when you're adding like that. All right, let's take a look at 13 here. So this one, they all look a little different. We've got a square root of 8, square root of 54, square root of 6. It seems like you can't do anything. But those are reducible. Okay, this square root of 8 here, I could look at that as 4 times 2. This square root of 54 is actually 9 times 6, and I can't really do anything with this. Now, why am I doing that? Because these are perfect squares that are factors of 8 and 54. I can take the square root of those perfect squares. So this here turns into minus 2 square root of 2 after taking the square root of 4. The square root of 9 is going to be 3 times the negative 2 makes this a minus 6 square root of 6, and then plus 3 square root of 6 at the end. So now I do have two like terms, 2 square root of 6's. So I'm just going to do a minus 6 plus 3, which is a minus 3 square root of 6. And the minus 2 square root of 2, can't do anything with it. Again, not a like term, so you just leave it. Okay, we're not multiplying, so we can't put these together in any other way, just adding and subtracting. All right, this one down here is two approaches we could take with this. I'm just going to notice right off the bat that these are the same. Square root of 45 times the square root of 45, that could be 2 square roots of 45 plus the square root of 12. Okay, now let's look at how we can simplify square root of 45 and square root of 12. Perfect squares that are factors of 45, well, I know 9 times 5 is 45, and 4 times 3 is 12, so those are perfect squares right there that I can pop out of there. Square root of 9 over here is 3, multiply it by the 2, gets a 6 square root of 5, and then this over here, square root of 4 is 2, so that's 2 square root of 3. That's as far as you can go with that one. All right, similar problem down here. I look at this and I see right off the bat, I got a couple square root of 6's, but I have these that I'm pretty sure I can simplify those. We got the 54 again, we just did one like that. That's 9 times 6. Square root of 6, can't do anything with it. Square root of 20, though, is 4 times 5. There's two perfect squares in those, and then we've got the square root of 6 at the end. So this first one then becomes 3 square root of 6 plus another square root of 6 plus 2 square root of 5. Square root of 4 there is the 2. Square root of the 9 here was the 3. And then plus the square root of 6 there. So it looks like I have a bunch of square root of 6's here that I can put together. So I've got, remember, this is a 1 square root of 6 here and a 1 square root of 6 here. So that's 3 plus 1 is 5 square root of 6's plus 2 square root of 5. Moving on here, getting into some multiplication. So I'm going to write out the middle step for this, but really what we're doing here is we're distributing this to each of these. So it's going to be 4 square root of 5 times 3 first, plus 4 square root of 5, 4 square root of 5 times square root of 5. That's just the distribution process there. So on this first one, all I can put together is a 4 times 3 there. That square root of 5, nothing I can do with that. Just 4 times 3, which is 12 square root of 5. This last one here, whenever you take a square root of something times itself, you kind of have this general rule. Square root of x times the square root of x is just equal to x, which means square root of 5 times the square root of 5 is just equal to 5. So we got 4 times 5 there. 12 square root of 5 plus 20 is your answer. This one here, could do this one or two ways. You could just say, oh, I'm going to multiply these together and make square root of 8. But you know what? Square root of 4 is 2. Let's just rewrite that as 2. And then bring the square root of 2 down. And that's it. You can't do anything more with that. So that's pretty simple. This one here, you got to FOIL things out. Okay, so you definitely see one like this on the exam. I want to make sure you can combine some different properties here that we've learned in the past. So it's going to be this times this, like this. Just distribute that first. You call it formula, I like to call it double distribution. So square root, we're going to say 3 square root of 3 times the square root of 3. That's the first one. And then 3 square root of 3 times the 1, which just makes 3 square root of 3. Can't really do anything with that. Now we move on to distributing the second one. So I'm going to take the plus 2 times this and then times this. So that's plus 2 square root of 3 and then plus 2. There's that situation there again of a square root times itself. So that here just turns into 3. So we got 3 times 3 plus 3 square root of 3 plus 2 square root of 3 plus 2. This is going to be 9, and I'll add that to the 2, makes 11. These two in the middle can get together. 3 plus 2 is 5 square root of 3, because those are both common terms there, like terms. All right, now we're getting into some exponents, so I just want to simplify this. Remember, when you are putting exponents together and you're multiplying them like this, you add the exponents of like bases. So I'm going to add basically 2 plus a half, which is 2.5. But we want to write that top heavy, so that's equal to 5 halves. Remember, to do that, you just take the 2 times 2 is 4 and add it to the 1 on top, makes 5 halves. So that just means this problem here is 3p to the 5 halves. You can't do anything else with that. You can think of it as a 1 there, so the 3 just comes from 3 times 1. It's like two separate problems. You're multiplying the numbers, you're multiplying the p's together. All right, here's one where we got to do a little PEMDAS first, because I'm raising a power to a power. PEMDAS meaning parentheses, exponents first. So here I am with my exponents. I got to put those together. But remember, the rule is when you're raising a power to a power, you multiply the exponents. So I'm really going to do this. 3 halves times 3 halves, which is 9/4. So this here just turns into k to the 9/4 times k squared. So now I'm multiplying like bases, so I got to add the exponents then. So I'm going to take that 9/4 and add 2 to it. But it might be easier to rewrite that 2 as 4 over, or sorry, it's going to be 8 over 4. 8 over 4, because that's the equivalent of 2 with the common denominator of 4. So add those up, you get 17/4. So that is the power of your final answer, k to the 17/4. All right, these ones here, you're doing a little bit of division with them. The direction said your answer should contain only positive exponents, no fractional exponents in the denominator. We'll see how that turns out for us here. So this first one, well, this is actually pretty easy. Don't have to really do a whole lot of work here, because this chunk right here is something divided by itself. X to the 1/2 divided by x to the 1/2. What happens when you divide something by itself? Equals 1. So this is just 3. That's all that's left over. Nothing too fancy there. Down here, this one's a little bit different. Okay, that 4, it's staying put down there. Okay, there's no way I can reduce that. That's the only number I have here. Technically, there's a 1 on top, but yeah. So this here, though, this is b to the first on the bottom. Got a b to the 7/4 on top. Remember, when you're dividing like bases, you subtract the exponents. So this is really 7/4 minus 1, trying to figure out what that is. Or 7/4 minus 4/4 with the common denominator, so that is 3/4. So this ends up just being b to the 3/4 on top. All right, solving equations. These, the main thing you're going to do is, number one, isolate the radical. If there's 2, get 1 on each side, like I have here. So this one's already all set up for us. But the big thing on these to remember is to get rid of a square root, you square both sides. Remember, you got to do it to both sides. So this one's really easy because it just drops off and turns into 3a plus 2 equals a plus 6. It just poof, makes it go away. And the rest of this is pretty easy to solve. Bring my a's to the left, it's 2a. Bring my numbers to the right, that's 4. Divide both sides by 2, and a is equal to 2. It's not a bad idea to plug these back in and check them. And always into the original, though. And in this case, it works. You get square root of 8 and square root of 8. Let's try another one of these. So this is a case where you want to bring everything to one side first. So I'm going to subtract 2 from both sides. I want to get this thing by itself, the square root by itself. So we have 6 minus x here equals 0. So now that's isolated. Do the same trick we did before. Square both sides. And it turns out we get just 6 minus x equals 0, because 0 squared is 0. Solve it the rest of the way. You get 6 equals x, and that's your answer. All right, let's try another one of these. This one's a little bit more complicated. I already have the square root isolated, so I'm just ready to square both sides. Just don't forget to square the x. So we get x squared equals 30 minus x. So you're going to have to do a little factoring on this one. This is a quadratic. Anytime you see that squared term there, means it's quadratic. You got to basically set it equal to 0. And then we might have to factor this. So this would be x squared plus x minus 30 equals 0. All I did is just brought these two things to the other side. And this is factorable. We get x plus 6, x minus 5 equals 0, because that 6x and minus 5x, they do combine to make a plus 1x there, and 6 and negative 5 are factors of 30. All right. And if you're having trouble with the factoring aspect, that's kind of a separate thing, and you can ask for some extra help in that regard too. But then we got to set each of these equal to 0. So if we did that, x would equal negative 6 and 5. One of those is extraneous, though. Let me show you what that means. Up here, if you're looking at this, if you plugged in the negative 6 to this x here, you'd have a negative 6 equal to a square root. It's impossible to get a negative out of the square root. So that means the negative 6 is extraneous. The 5 does work, though. So your answer is just 5 with the negative 6 being extraneous. So you can just put an x through it like that, and that's fine. All right, let's try some other things here. Getting into inverses, find the inverse of each function, then graph the function and its inverse. I'm probably not going to have you do the graphing part, but let's do the, we'll still maybe take a look at them, but on the test, probably won't have you do that on the exam. So find the inverse. Remember, the trick for that is to first rewrite this as y equals negative x plus 1. Then you swap the x and y in this. So you put the x here, you put the y where the x was, and then you want to solve for y. So that means I'm going to bring this 1 to the other side. X minus 1 equals negative y. Multiply everything by a negative to get rid of the minus sign on the negative. So this turns into negative x plus 1 equals positive y. So that is your inverse of f of x, and negative x plus 1. And just to look at the graph, how this will look on here, putting both on here at the same time. So the first one, putting f of x on there, it is going to start at 1 with a slope of negative x, so it's going to have a slope of negative 1 right here. So let's look at something like this, if I can draw a straight line. All right, and then if we go to this one, well, gosh, it's the same exact thing. So if the test for these is, does it have symmetry across this line, y equals x? And indeed it does. It flips exactly across it. Okay, so sometimes it happens. You have inverses that are exactly the same like that. All right, I'm going to do another one of these just to show you that these can be a little bit different. I'm not going to graph this one, but we'll do the inverse part of it. So this, again, rewrite it. Y equals 3x plus 6 over 7. Swap your x and y between these. So I'm going to make this x equals 3y plus 6 over 7. So if you have a fraction like this, you want to get rid of that 7 first. So I'm just going to multiply both sides by 7. So this turns it into 7x equals 3y plus 6. Gonna subtract the 6 from both sides, so that makes 7x minus 6 equals 3y. Divide everything by 3, and that is your answer there. This right here. So that is your f inverse of x equals 7x minus 6 over 3. All right. Find the inverse of each function. Just did a bunch of basically the same thing we're just doing, but I'll go through the odds here again just for some extra practice. So I'm going to change this into y, swap x and y. So this turns into x equals the cube root of y minus 2 over 2. How do you get rid of a cube root? Not cube root, but fifth root. You got to take the fifth power of everything. So I'm going to take this side to the fifth power, this side to the fifth power. So it turns into x to the fifth equals just y minus 2 over 2. Get rid of the 2 by multiplying both sides by it. And then I'm going to have to add a 2 to both sides, which makes this 2x to the fifth plus 2 equals y. Equals y, which is our g inverse of x. That guy right there. Okay. So that was a little bit more difficult. Let's take a look at one where the x is in the denominator, like this one right here. Swap our x and y. So this is x equals 2 over y minus 3. So you got to bring that 3 to the other side first, adding it. So x plus 3 equals 2 over y. I can't have a y in the bottom of the fraction, so I'm going to multiply both sides by y. So I end up with this y, and x plus 3 equals 2. So don't multiply this out right here. What you want to do is divide both sides by x plus 3. And that gets the y by itself. So this right here is your f inverse of x. Okay? Stating whether given functions are inverse is probably the easiest way to do this is to plug one inverse into the other and see what happens. The first one's, this is probably a little bit more difficult than I'm going to give you. Let's do one of these other ones. I'll look at number 46 here. And so the idea is if you plug in f of g of x, do the composition function. If it's equal to x, that means they're inverses of each other. So let's try this out on this one. And remember, this just means f of g of x, like this, okay? So if I do f of g of x, that'd be f of x minus 3. If I plug that into f of x, so anywhere I see an x in f of x, I replace it with an x minus 3. But I still keep the plus 3 at the end there. And I simplify it. Well, minus 3 plus 3 equals x. It checks out. That's all I'm looking for. If it equals x, then yes, they are inverses of each other. All right, let's try another one down here. Let's do this one, number 47. So I'm just going to jump right into, I'm going to reverse it though. Let's try putting f of x into g of x, because it doesn't matter which order you do it. Both should work, okay? So if I'm plugging f of x into g of x, that's g of negative 3 minus x over 3. So I'm going to plug this into this x right here, anywhere I see an x in the g of x. So it's going to be equal to negative 3 times all this, negative 3 minus x over 3, and then the rest of it. So this was the x here. Now I'm going to put the minus 3 on there. Just let's distribute. Well, these cancel out here. So it's really just a negative 1 times all these things. So that's going to be a positive 3 plus x minus 3. Those cancel out, and it is indeed equal to x. So it checks out. This is also a yes on this one. So if it didn't equal x, we'd say no, they are not inverses of each other. All right, let's do a couple graph sketches, and this will finish this out pretty much. So sketching the graphs here, you could also rewrite this as the square root of x plus 2 minus 4, put the minus 4 at the end. So the easiest way to do these is to do the x minus h plus k format. So your h in this case is a negative 2, because it's the opposite with the x minus h, and our k is a minus 4. You don't have to do the opposite of that one. So that's kind of your starting point. You're going to start at negative 2, negative 4 down here. And if you need to plug in a few points to get the rest of it, that's fine, but it's really just a sideways parabola, which means if you're starting at this vertex here, you go up 1 over 1. You go up 2 over 4. You'd go up 3 and over 9. So it's going to have this shape to it. But if you plug some numbers in, and in this case, the numbers you want to plug in, you want to choose numbers that are going to give you perfect squares, like negative 1. Because if you plug in negative 1 into this, you get square root of 1 minus 4, which is just negative 3. So that's this point right here that I already marked on here. And if you wanted to do the next perfect square, well, what would you plug in here? To get a square root of 4, you'd want to plug in a 2. So it ended up with the square root of 4 minus 4, which is negative 2. So that's this point right here. And really, you don't probably need any more than that. You know, if you went up to the next one, you'd want to get the square root of 9 out of this. So you go up to 7, and you get out of that negative 1. That's where this point was, way out here. All right, so that's kind of the general idea for these. That's the general shape they should have, but when in doubt, plug some points in. Just remember, you don't want to plug in points in a square root that are going to give you negative. So really, the lowest you could go with that was the negative 2, which is why that's the starting point. You go below that, you're taking square roots of negatives, which you can't graph. Let's do another one here. This one I'll do a little bit faster. Let's jump right into the x minus h part. Whoopsie. X minus h. So our starting point is going to be -1, 5. -1 comes from that. The opposite of that, +5 comes from that. So -1, 5 is right here. And if you plotted a few points, you'd end up with these guys here, and it would look like this. All right. And well, that's it. So just one, I guess, last general rule of thumb for these types of problems. Focus on what you can plug in and also what you can't plug in. You can't go below a -4 on this one or else you get negative. So that kind of gives you your starting point if you did want to pick some points to plug in. -4 is the lowest you can go, and then you can go up from there, -3 and whatever. All right, well, good luck.